So your job in mechanics is to try to predict or explain motion. A lot of times we spend a ton of time talking about constant force motion, and there's a reason for that. Constant force motion allows us to be able to predict the velocity and the position of an object exactly. And we're going to talk a little bit about that in this screencast, or in this video, as well as talk about how we coordinate these mathematical descriptions with some more graphical descriptions. So what we start with is the momentum principle. That's what I have here. I have it in its derivative form, but I also have it in its update form, which we talked about in one of the last screencasts. So let's ground this a little bit. So what we're going to try to do is predict the motion of a fan cart. So here's a track. Here's the fan cart. Here's a fan. And the fan is turned on so that there is a force due to the air to the right. And as you well know, there's an interaction with the fan cart and the earth that pulls it down. And as a result, there's a track force that pushes up on the fan cart. Now these two forces are equal. They're in opposite direction, but they are not Newton's third law pairs, as we'll talk about later. They are the result of interactions with different objects. But what you can see here is we have a diagram that helps us describe the net force, the sum of all the interactions on the fan cart. So we're going to add up those forces, and if we do that, we're going to find that the net force is simply the force due to the air, because the track force and the force due to the earth are, as I said, the same size but in opposite directions. Now the other thing that we need here is a coordinate system to tell us how we're going to do the prediction. So we're going to call to the right plus x. Now we'll take this prediction equation for the momentum and we'll make it a one-dimensional equation. So we're going to talk about the momentum change in the x direction. And that's the net force times delta t. Now that net force, as we said, is the force of the air. So we can actually get rid of this and make it very concrete and say that's the force of the air. One thing that we're able to do, because we know that the fan cart is not going to move much anywhere near the speed of light, we can use the definition of the momentum, or the approximate definition of the momentum, rather, to change this equation into an equation that predicts the velocity of the fan cart. So we'll go ahead and do that now. And what we find is an equation that allows us to predict the velocity of the fan cart in the x direction as a function of time. It contains this piece here that is the force of the air divided by the mass of the cart. That's the acceleration that the cart experiences. We can graph this really quickly to get an understanding of what it means for this motion to occur. So I'm plotting here the velocity in the x direction over time. So the fan cart starts at with some initial velocity, and it moves to the right, and it does so linearly through this equation here that we understand, up until some final velocity. Now the slope of this line is precisely the acceleration in the x direction. It's the net force divided by the mass. It's the force of the air divided by the mass. That comes from this part of this equation here. The other thing you might notice is actually the area under this curve is the velocity integrated over some time interval. So it turns out that the area under this curve is actually the displacement of the object, that is the fan cart. So we've been able to predict the velocity of the fan cart. Now we're going to predict the position of the fan cart. And we're going to go immediately to the one-dimensional description of the position update formula, which is that the initial location plus the displacement, the average velocity times delta t, is equal to the final location of the object. So the thing that you need to be able to do here is actually tell me what the velocity, the average velocity in the x direction is going to be. So what we've used previously is this definition of the average velocity in the x direction. It's the displacement divided by time. Well, but that's how we got this equation, so that's not very useful. Another way of thinking about the average velocity is that it is actually approximately the arithmetic average, so the final plus the initial divided by 2. And this is exactly why you can predict motion in a constant force situation exactly, because this approximation is not an approximation for constant force motion. This is actually exact for constant force motion. And so because this holds exactly, we can predict exactly where the object is going to be. So I'm not going to do the math here. What I'm going to say is if you plug in this final velocity that we got from our velocity update formula into this equation and then back into here, it will result in a prediction equation, which is on the notes, that looks like this. It's quadratic in time. It has information about the initial location, the initial velocity, and the force that the cart experiences. You might have seen this before as a kinematic equation where this was the acceleration. Now, if we wanted to graph this, we could do that pretty easily, because we know that it's quadratic in time. We know the cart moves to the right. And so starting at its initial location and ending at its final location, the cart has some profile. The graph has some profile that looks like this. One piece of information that's pretty cool that you can get out of this is this idea of the average velocity using the change in position divided by the change in time, or rather the slope of this line. The slope of that line is precisely the change in position over the change in time, which is the velocity at any instant. So what we have here is a set of equations and some graphs that help us to try to understand constant force motion. As I said, this is the only time that you'll have an exact equation that describes the motion of systems. And it's precisely because we can treat this approximation as exact for constant force motion.